The original plan to get Starship to the moon required up to 30 separate rocket launches just to fill the tank. 30 launches for one mission. Every single one of them carried nothing but propellant, transferred in orbit through a process that had never been demonstrated at scale in the harshest environment humans have ever attempted to operate machinery. Engineers called it the most complex logistics chain in the history of space exploration. Critics called it an impossible schedule. And NASA, watching the delays pile up and the timeline for returning humans to the moon slip further and further into the future, finally ran out of patience. On October 2025, the agency did something it had never done to SpaceX before. It told the company to go back to the drawing board and come back with something simpler. And what SpaceX came back with is one of the most consequential design pivots in the entire history of the Artemis program. The new plan cuts the number of refueling launches to fewer than 10, from up to 30 to fewer than 10. That is not an incremental improvement. That is a fundamental rethinking of the entire mission architecture from the Propellant Depot outward. And the engineering decisions behind that shift reveal something important about how SpaceX is now approaching the challenge of lunar exploration, not as a maximally capable system built for the long term, but as the fastest possible credible path to putting American astronauts on the surface of the moon before anyone else gets there first. To understand why the refueling problem became so critical, you have to understand the physics of what Starship is trying to do. The version of Starship designed as a human landing system for the Artemis program, known as Starship HLS, is a massive vehicle. It is over 40 meters tall in its lander configuration, carrying a habitable volume that exceeds the Apollo lunar module by more than double. It can deliver enormous amounts of cargo to the lunar surface, but that capability comes at a cost. The propellant required to push a vehicle of that mass from low Earth orbit all the way to the moon, perform a controlled descent to the surface, lift off again, and return to lunar orbit is an enormous quantity. Starship's tanks simply cannot carry enough propellant to do all of that from Earth alone. The vehicle needs to be filled in orbit after it gets there. The original architecture to solve that problem was technically elegant, but operationally staggering. A dedicated depot Starship would be launched into orbit first and parked there. Then, in a sequence of tanker flights, each Starship tanker would launch from Earth carrying propellant rather than payload, dock with the depot, transfer its propellant, and return to Earth to be reused. The depot would gradually fill up over a series of these tanker flights until it held enough propellant to completely refuel the HLS lander before it departed for the moon. The number of tanker flights required, based on estimates of propellant transfer efficiency, boil-off losses from the cryogenic fuel evaporating over time in space, and the overall volume needed ranged from a conservative figure of 14 in SpaceX's own documentation to estimates as high as nearly 30 from independent analysts. That number was always the plan's most vulnerable element. 14 to 30 Starship launches in sequence, each one requiring a successful flight, a successful docking, a successful cryogenic propellant transfer in microgravity, and a successful return to Earth before a single astronaut could begin their journey to the moon. Any one of those flights failing changes the entire downstream timeline. And in the background, the orbital cryogenic propellant transfer technology underpinning the entire approach had not yet been demonstrated in space. The full ship-to-ship demonstration, where two separate Starships would dock in orbit and one would transfer propellant to the other, had been planned for 2025, slipped into 2026, and as of March 2026 had still not occurred. NASA's frustration with this situation came to a head on October 2025. The agency's acting administrator, Sean Duffy, called publicly for a major acceleration of the lander development program. And in the most significant pressure move it had applied to SpaceX since the original HLS contract award in 2021, NASA reopened the competition for the Artemis lunar lander to allow Blue Origin's Blue Moon spacecraft to compete directly against Starship for the contract. This was not a symbolic gesture. It was a direct signal that NASA was willing to walk away from Starship as its sole lunar lander if SpaceX could not demonstrate a credible path to the required capability on an acceptable timeline. The deadline for revised plans was October 29, 2025. SpaceX responded with a redesigned concept that represented one of the most decisive engineering pivots in the program's history. The original Starship HLS was conceived as a maximally capable lunar surface presence vehicle. It included aerodynamic airfoils, a full heat shield, complex refueling system interfaces, and the structural provisions needed to support the enormous cargo capacity that the full vision of a sustainable lunar base required. All of that capability added weight. Weight requires more propellant. More propellant requires more tanker flights. The cycle compounded on itself, driving the mission complexity steadily upward. The simplified design strips all of that away. Gone are the aerodynamic airfoils and the heat shield that were part of the original configuration. The new lander is not designed to re-enter the Earth's atmosphere. Its job is to operate exclusively in the lunar environment, descending to the surface and ascending from it without ever needing the thermal protection that a vehicle returning to Earth requires. By eliminating those systems, SpaceX shed enormous amounts of mass from the vehicle. Less mass means less propellant needed to move the vehicle. Less propellant needed means fewer tanker flights required to fill the depot. The engineering cascade runs in the opposite direction from the original design's complexity spiral, each simplification enabling the next one downstream. The rendezvous orbit has also been changed in a move that carries significant implications for both efficiency and crew safety. The original architecture planned for the HLS lander to rendezvous with the crewed Orion spacecraft in a near rectilinear halo orbit, a highly elongated orbit that takes the spacecraft on a looping path out to nearly 80,000 kilometers from the Moon at its farthest point before swinging back to within 1,500 kilometers at its closest approach. The NRHO was selected as part of the Gateway Space Station architecture because it provides a stable long-term parking orbit with relatively low propellant requirements to maintain, but it is also a complex orbit to reach and maneuver within, and the abort options available to a crew in distress at the far point of an NRHO are severely constrained. SpaceX's simplified design switches the rendezvous to a low lunar orbit, a much simpler circular orbit at a far lower altitude, above the lunar surface. Low lunar orbit requires less total propellant to reach from Earth than NRHO, when the mission architecture is considered as a whole in this configuration, reduces the energy demands of the descent and ascent maneuvers, and provides significantly better abort options at every phase of the crewed surface operations. If an emergency develops on the lunar surface and the crew needs to return to orbit quickly, a low lunar orbit rendezvous is far more forgiving than the complex timing and trajectory constraints of an NRHO rendezvous. NASA's primary requirement for the Artemis program has always been crew safety. The interior of the redesigned lander has also been rethought from the astronaut's perspective. The original Starship HLS design presented a challenge that astronaut feedback highlighted early in the program. The vehicle is tall, very tall. Getting from the cabin at the top to the lunar surface far below was originally planned to require descending a ladder that would have stretched nearly 30 meters. That is not just an inconvenience. In a spacesuit, carrying equipment on the surface of a world with different gravity and terrain conditions than any amount of Earth-based training fully replicates, a 30-meter ladder descent is a significant operational and safety risk. The redesigned lander replaces the extended ladder with a mechanical hoist system that lowers astronauts directly from an airlock to the surface. The two airlocks on the new design each have more internal volume than the entire airlock of the Apollo lunar module, providing the crew with more space to don and doff spacesuits safely and reducing the risk of suit contamination from lunar dust during the pressurization cycle. The number of tanker flights required to fuel the simplified lander has been cut to fewer than 10. This is the figure that SpaceX and NASA have both referenced in public communications since the redesign was unveiled in late 2025. The reduction from up to 30 to fewer than 10 is the result of everything described above working together. A lighter lander needs less propellant for descent and ascent. A lower rendezvous orbit changes the total propellant budget. Simplified refueling interfaces reduce the losses that occur during each transfer. And the elimination of the mass associated with reentry systems removes a propellant penalty that had been present in every version of the mission architecture up to this point. Fewer tanker flights means a shorter overall campaign to reach readiness. A shorter campaign means a faster path to the Moon. SpaceX has been explicit about what comes next for the technical demonstration program. The company stated in October 2025 that two critical flight milestones remain before any HLS mission can proceed. The first is a long-duration orbital flight test, where a Starship is placed in orbit for an extended period to validate the systems that need to function reliably across days or weeks of spaceflight, rather than the hours of a reusability demonstration. The second is the ship-to-ship propellant transfer flight test, where two separate Starships dock in orbit and complete an actual cryogenic propellant transfer from one vehicle to the other. SpaceX stated that both of these tests are targeted to take place in 2026, with the exact timing driven by how the V3 architecture flight campaign progresses. The in-space propellant transfer demonstration is the most technically novel element still remaining on the critical path. Transferring cryogenic liquid methane and liquid oxygen between two spacecraft in microgravity involves challenges that ground-based testing cannot fully replicate. In a weightless environment, liquid propellants do not settle to the bottom of their tanks as they would under gravity. Managing propellant flow requires careful settling burns, precise tank pressurization control, and real-time monitoring of temperatures that can behave unexpectedly in space. SpaceX has modeled propellant slosh behavior extensively during docking maneuvers. The demonstration flight will turn all of that modeling into actual flight data. confirming or challenging every assumption the engineers have built into the refueling architecture. The competitive pressure from Blue Origin is reshaping the timeline in ways that benefit the program overall. Blue Moon represents an alternative path to the surface that NASA can now credibly consider if SpaceX continues to slip. The effect of genuine competition on SpaceX's engineering cadence has already been visible. The simplified lander proposal was submitted within a month of NASA's ultimatum. SpaceX's commitment to being the fastest path to the lunar surface has been tested and produced a concrete design response. What SpaceX has produced in the simplified Starship lander is a design that trades maximum long-term capability for immediate operational achievability. It is a smaller vehicle, a simpler vehicle, a vehicle with fewer things that can go wrong and fewer flights required before a crew can board it. It is not the Starship that was going to build a permanent lunar base in one mission. It is the Starship that is going to put 2 astronauts on the surface of the moon as quickly as the laws of orbital mechanics and the state of propellant transfer technology allow. And in the race to return humans to the moon before China achieves the same milestone, that trade-off may be exactly the right one. There's a broader context to this engineering pivot that the space industry is watching carefully, because the shift from 30 refueling flights to fewer than 10 is not just a logistical improvement. It is a fundamental statement about what makes a space program sustainable in the political and budgetary environment of the 2020s. The original architecture, requiring up to 30 tanker launches as a prerequisite for a single crewed landing, was always going to be vulnerable to political scrutiny when timelines slipped and costs escalated. Each additional tanker flight is another opportunity for delay. Each additional docking operation is another technical risk. Each additional month of cryogenic propellant sitting in an orbital depot, slowly boiling off despite the best insulation available, is another cost compounding against the program's budget. The simplified architecture changes that risk profile dramatically. Fewer than 10 tanker flights begin to resemble something achievable within the operational tempo of the V3 Starship program now ramping up at Starbase. With Pad 2 operational and a second orbital launch mount available, SpaceX has the infrastructure to run 2 simultaneous Starship campaigns. If the propellant transfer demonstration and long-duration orbital test proceed on the 2026 timeline the company has stated, the tanker campaign needed to fuel the simplified lander could realistically complete within a window that makes a late 2027 or 2028 crewed landing mathematically possible rather than aspirational. The geopolitical pressure driving all of this urgency cannot be separated from the engineering decisions being made. China's lunar program is advancing at a pace that NASA administrators have described publicly as genuinely concerning. The China National Space Administration has outlined plans for a crewed lunar South Pole landing before the end of this decade. At the lunar South Pole, where permanently shadowed craters contain water ice representing both a survival resource and a potential propellant feedstock. Being second is not a neutral outcome. It is a strategic loss with consequences extending well beyond the symbolic. The simplified Starship lander is SpaceX's answer to that pressure. Every component removed from the original design was removed in service of one objective: getting American astronauts to the lunar South Pole before any other nation. And the result is an architecture that, for all its reduced capability relative to the original vision, is the most credible engineering path that currently exists to achieving that outcome before the middle of this decade. The moon is waiting. The propellant transfer demonstration is the next critical gate. And what SpaceX has built in its simplified lander is a vehicle that the physics, the engineering, and the timeline of the program now say can actually get there.